Oh, John Wick is entered. Okay, so today we're going to be looking at a presentation on systems and universal system model. It's actually sort of interesting. I'm going to be introducing you to the Unit 3 assignment, components of a system. So we're going to be learning about systems, and we're going to have a project doing what with systems? Identifying the good parts and the bad parts. It's a lot of what we do for technology. All right, we've got a good showing today. Oh, I didn't let in a little time. All right, so what is due is our warm-up. Unit 2, impacts of technology, society, economy, and environment were due. So that's our project looking at the labor-saving device. I have some exciting ideas about labor-saving devices. And Leslie. So good to have Leslie with us. Okay, and our new assignment, the Unit 3 assignment, Components of a System, is going to be due on the 17th. So that is going to be in the next quarter, okay? I think I'm actually going to put our quiz into the next quarter too, not our quiz, our vocab for components of a system. We have a mandate to try and reduce the number of assessments, et cetera, to try and improve your mental health. So the fact that we do mostly assessments is a little problematic. Because our quizzes and our projects are both assessments, just our warm-ups are practice prep. When is Q2 over? Q2 is over January 29th, I believe. The interim is the 15th. That is next Tuesday. So what this means for us, so here in our scheduling, so let me first say that our next assignment, we're gonna have about 10 days to work on. That will put it in the next quarter. It'll let us think about this and have a little fun. I'm hoping everyone had a little fun dreaming up your invention that saves 10 times the labor on whatever it was you decided. I've started thinking about these and I came up with a bunch that I think would be really fabulous and fun. So if you have had trouble coming up with an idea, I think I'll brainstorm a little at the start, okay? Interims, if I could put this on here, are the 15th. That's when my grades are due. That means that any late assignments are due by Friday. Ideally, get anything that you need to get in by Friday. I have sent progress reports to you and your parents. If you are in danger of failing, which quite a few people are, remember, our vocabulary, do assessments to get your grade up. Warm-ups are great, but they're only worth 10% of your grade. So assessment points are worth 9 times as much to your grade. Do your vocabularies. Those are easy. You can look in the presentation for the words. It's not hard. You just need to find a picture to put in there, okay? If you've done those, do a project. We just did a project that is not that difficult. Imagine a labor-saving device that does 10 hours of work in 1 hour's time. What are 3 benefits of that device in full sentences? And what are 3 negative consequences of that device? That's all you got to do, 20 points. that is going to really help your score. That will probably get you passing. So while I'm on this, I had the idea, what if you could clean all the glass windows on a skyscraper in 1/10 of the time? Create some crazy device that cleans the windows 10 times faster. What would that mean? What do you think the contracts are to clean the windows on skyscrapers? I mean, that has to be huge. What about painting? What about a device that would paint a house in 1/10 the time? What about a device that would roof a house in 1/10 the time? These are just a couple ideas that popped into my head, but they have a lot of impact. Where originally when I was thinking about it, I was like, what could I do? How could I make this work? But the idea that you could paint your house 10 times as fast, it would be much cheaper. Paint is so important to preserving wood and features of your house. There's a lot of good things and bad things. What would be a bad thing from having a device that painted your house in 1/10 the time? In my mind, you're going to be using more paint, and we're going to have to extract more natural resources in order to create that paint. So here's a weird example. Apparently, due to a new administration rule, miners are going to be able to mine on the edge of Okefenokee Swamp. That is down in Georgia, I believe. Is it Florida? I think Okefenokee. This is because they have changed the definition of what a wetland is or what a waterway is, which is really tragic. Wetlands are one of the most productive areas that we have on our continent for biodiversity and animal life. Destroying wetlands is destroying our country. Surprisingly, the people who have contributed the most to wetland protection are probably conservatives. And that is because what was created to preserve wetlands were duck stamps. People who were duck hunters had to pay $25 to have their hunting license, renewed or whatever, so they could go duck hunting. All that money went into wetland preservation. So surprisingly, it is duck hunters that are responsible for most of our wetland conservation. But wetlands are very precious. So the mine that is being proposed in Georgia on the border of Okefenokee is a titanium mine. Titanium is it's not a precious metal. It is relatively rare, and it is a big component of white paint. I know because I lived in LA and I have come across a truck that rolled over carrying titanium white. It's when I decided that coffee whitener is probably made out of titanium white because it looks very much like coffee creamer. All right, that's enough on that. If you haven't done that last project, get that in. Also, for our project that is due the 17th, focus more on projects that were due in this quarter. That one is going to be due in the next quarter. You will have time to make that up or pick that up. Any assignments from this first half of the second quarter, please get them in. I have a deadline for Friday because I need time to get everything reviewed, organized, and into the system. As we know, there are issues sometimes between Canvas and Synergy. Our objective today is that you will recognize the difference between open and closed loop systems, determining the costs and benefits of closed and benefits. That's pretty bad English. I was trying to say that determining the costs and benefits of closed and open loop systems. That's what that's supposed to read. Defining system thinking. Okay, let's get into our presentation. So, hang on, let me just show you a couple things that are in the module. Well, actually, let's, hang on. Let me show the module. There we are, and you're seeing it. Let's do the warm-up, but I just wanted to say, so here's the vocab quiz. This is probably dated wrong. I need to adjust this date. I'm going to make this This vocab quiz is actually going to be part of the next vocab quiz that we do. I'm going to put two together because we need to reduce the number of assignments. What is in here is the Unit 3 assignment, the components of a system. We'll go over that. There's a video on open and closed loop systems that we'll watch. Let's do our warm-up. I will call on someone for this. I have my beautiful random calling app now. Okay, so what are constraints for technology? Okay, that's our big question. What are constraints for technology? All right, I'm going to call someone. Let's see. Jackson Blanco Prudencia. What are constraints for technology? Are they wrappings on blueprints, US regulations, or nature's limits on a design? Jackson, can you answer that? Jackson? You might not be able to hear. Or catch-all. Hang on, I'm just gonna see. Jackson's here. Okay, let's try another. Ramon Nelson. Oh, actually, I know Ramon isn't here. Ruby Borskowski. Can you tell me what are constraints for technology, given the choice of wrappings on blueprints, US regulations, or nature's limits on a design?
Me, sir.
Oh, there's Jackson.
Yeah.
What do you think?
It's the number 3.
Number 3, brilliant. Thank you, Jackson. Ruby, do you agree?
Yeah, I was gonna say nature's limits on the design.
Yep. Perfect. All right. Everybody was paying attention last week. Great job. Thank you, Jackson. Sorry to miss you there for a moment. Okay, so back we go. Let's get into our presentation. So we're going to present. Everybody, we're seeing this full screen, correct? Anyone? Thumbs up, full screen?
We can see.
Okay, thank you. Today, we're going to be looking at systems and the universal system model. We'll also be understanding system thinking. We're probably not going to get through this because I want to talk about the project and get you thinking about that. Okay, systems and universal systems model. The core concept, oh, we lost Layla. The core concepts of technology highlighted by the technology content standards, that is a set of standards that have been established, are systems, resources, requirements, optimization and trade-offs, processes and controls. Whoops, what the heck just happened there? Wow, that was interesting. Chrome just sort of blew up for a moment. All right. This lesson will focus on systems and the universal systems model, thus opening the door to systems thinking. I want to go over this core concepts of technology. Highlighted by the technology content standards are, these are the fundamentals for creating technology. You need to understand systems. You need to understand resources. You need to understand the requirements for whatever you're building. Those will be both technology design requirements and engineering design requirements, right? So those can both go in there. Optimization and trade-offs. So this is where I was talking with the class before about an interesting idea for optimization and trade-offs. Optimization and trade-offs is when you are in that research and design mode. You're researching. You are thinking about how you're going to create a better product. So what was one thing, this would have been back in probably the 90s, early 2000s, what was one thing that was holding back development of smartphones? Hang on, I'm going to actually turn off my background because it just causes trouble if I'm showing you things. Okay, hang on. Oh, now we're going to actually see me. We need a little hair and makeup. All right. So with the cell phone, what was one of the major things that companies trying to make them needed to overcome in the design process? Can anyone think of what was one major hurdle? And I will say you are looking at it right now on my phone. What's the problem with the smartphone? Where do you keep it? You can put it in the chat or sing out. Where do you keep your phone typically? I keep mine in my front pocket. Okay, what also lives in my front pocket? Anybody? What do you keep in your front right pocket? That's where I put my phone. I have keys. What's that?
Oh, I don't really have pockets that can hold stuff, so.
All right, keys. Yes, Nestor has added my critical ingredient. What was the problem that the cell phone designers must have been talking about in their research and in their experimentation with the glass on a cell phone when I put it in my pocket with my car keys? What happens to the glass on my cell phone when it goes into a pocket with car keys? See, you can even hear me scratching the glass. It does not scratch. Now, that is the innovation. Any regular glass would have scratched. Glass scratches. When I take car keys and scratch glass, it's going to scratch, even though it is very, very hard. So what did they have to do? What did the first brilliant person come up with as an idea for glass for my cell phone that will not scratch? What would that need to be made of? If I didn't know any better. If I'm a technologist, right? I'm a tech designer. I'm going to make the glass in my cell phone be totally scratch proof, but it hasn't been invented yet. So what's my thought for what could I use to make a clear sheet that would not be able to be scratched? What materials, what resources would I need to make that? This is an imaginary thing because it would cost you thousands and thousands of dollars. Just as an engineer or designer thinking about what could I make my cell phone glass from that would not get scratched? Anybody have an idea? What cuts glass? If I have a piece of glass and I need to cut it, I'm going to use a tool that has what embedded in the blades? I need what gemstone to cut
Is it
glass?
diamond?
You need a diamond, right? You are. So as a technological designer, I said, I want to have the glass in my phone be diamond because that way it'll never scratch, right? I'm going to have a diamond screen cell phone. And it's going to be a big diamond too, because I need a slice of it for my screen. Okay, is that doable?
No.
No, because it's going to be too expensive. It's going to be too difficult to work with. But is the idea valid? That if I could put a slab of diamond on my cell phone, the screen would not be scratched. Is my concept valid? That if I used a diamond screen, my cell phone screen would not be scratched?
Yep. It's a
Okay.
valid concept.
That's a valid concept. So What did the brilliant engineers at Apple do to figure out how to optimize the glass in their iPhone? They had to make trade-offs for that optimization. Initially, we say diamond glass, we're not going to be able to make diamond glass. All right, diamonds are too expensive. Somebody did figure, so this goes to the resources. If the resources are not available to you, so I can't get cheap giant sheets of diamond to put into my phones, what am I going to do? Just put in regular glass? That's not going to work. I need to create a new resource, something that has never existed before. And I'm going to do that through thinking about what does exist and how I can make it better. And somehow they came up with a formulation to create. Does anyone know what the glass in your iPhone is called? It is a very special kind of glass, and it is only made at certain factories. I believe Foxconn in beautiful China is one of them. Does anyone remember what the name of the glass in your iPhone is? It's the name of a certain gemstone. What gemstone is it? Is it diamond glass? Oh, here we go. Let's go A, B, C, and D. All right. So A is diamond, B is ruby, C is sapphire, and D is corundum. Which one? On those. Sapphire glass. This is called sapphire glass because they were able to innovate a process using rare earth metals, etc., to create a crystalline structure that is very similar to sapphire to use for the glass in the phones, because sapphire is basically the same as diamond. I think it's a little teeny bit less hard than a diamond, but just as a trick question, corundum is also the name of sapphire and ruby. Rubies and sapphires have the same chemical composition. They are just different colors, okay? And don't get me into that, it gets very confusing. So just think of that as a model of how a big company had to come up with a brilliant idea. We're going to use diamond because it doesn't get scratched. See that the resources were not available, that it's too expensive, and then spend a lot of money to optimize a process that would create something that wasn't quite as strong as diamond glass, but just about, and made a relatively scratch-proof phone glass. So that is just one way of understanding this process. So you've got optimization and trade-off. You have processes, the formulation and extrusion of sapphire glass, and controls. Does my sapphire glass that I'm making scratch? Gee, if my sapphire glass scratches, there must be something wrong with my formulation because this is not sapphire glass. Sapphire glass would not scratch, okay? You need to test your products. You need quality control. You need risk management. Those are controls on your process. All right. As you can see, I kind of like this one. So here's one of our words, system. A system can be defined as a group of interrelated components designed collectively to achieve a desired goal. Okay, so a system can be defined as a group of interrelated components designed collectively to achieve a desired goal. So the first thing that came to my mind is systems can either be open loop systems or closed loop systems. Open loop systems or closed loop systems. Just thinking back on a regular system, it makes me think of a farm for some reason. A farm has a group of interrelated components designed collectively to achieve a desired goal. You have machines that plow fields. You have machines that plant fields. You have machines that harvest fields. Those are a group of interrelated components designed collectively to achieve a desired goal. Planting and harvesting crops over the course of a year. That is a system. A farm is a system, all right? I'm going to leave this open and ask, can anyone give me an idea of what an open loop system is? I'm guessing you haven't heard of this, so it's not surprising you don't know what it is. But I was just wondering if anyone could guess at what an open loop system might be. And you can cheat and read what's on the screen. What is an open loop system? Anyone? Okay. So an open loop system, I'm just going to tell you in plain English to start with, and then we'll go into the text, which of course is much more convoluted. An open loop system is a system that has no control on it. It has two speeds, stop and go like hell. Pardon my French. So the control on an open loop system is a human. A human has to observe that something is happening and do something as a result. We are the control systems. This, excuse me, my collar's all terrible. That's bad. This is a great way of determining, is this an open loop system? Does a human have to do something to regulate the system? If they do, that is probably an open loop system. So an open loop system is a control system that has no means of comparing the output, the result of the operation of any system, with input, something put into a system, such as resources, in order to achieve a result for control purposes. Okay, my fabulous example for this is very simple. I have a house and I'm a human, I'm a Homo sapien, so I need water. I also have a cute little dog that needs water. I purchase my water from the county. The Montgomery County has a water system and they put a pipe into my house with water. That is my input, okay? It's a control system that has no means of output. The result of the operation of any system. With input, okay, I have input. I got water coming into my house. If I open the spigot for my water, water pours out the spigot. If that keeps happening, is Montgomery County going to cut off my water because they just noticed that 5,000 gallons of water was used in the last hour, which doesn't seem like normal usage? No, they are not. There is no control on my water pipe other than they put a meter on it so they can charge me for however much water comes through that pipe. I can open, a human needs to open the valve or close the valve. So say I left my bathtub running upstairs in my bathroom. I go down and start making dinner and totally forget about my bath. When I see the water starting to come down my stairs from upstairs, what am I acting like in this system? I am the control, but I am also the feedback system. I am seeing water, and that is telling me, oh my God, there is a whole lot more water upstairs about to come down the stairs. I better do something quick. So I run up and turn off the water and then start mopping it up. Control of open loop systems requires human intervention. An example of an open loop system is a microwave that requires a person to determine if the food has been heated to the required temperature. How do you do that? I put a big bowl that I had in the refrigerator in the microwave and I nuke it for a minute. Do I want to eat it right now? Or what do I do? What do you do when you heat up a cold bowl in the microwave? Can anyone tell me? I'll call on someone. This is a good one.
It warms up.
But if it just came out of the refrigerator and I only turned the microwave on for a minute, what's the problem with that bowl of food?
It's still gonna be a little bit cold.
Right, so I gotta like stick my finger in there and see, is it still cold in the middle? Ooh, it is. I better put it in for another 2 minutes. I am the feedback loop. So the microwave, it like I said, microwave has 2 speeds. Well, you can apparently adjust it to a lower power setting, but nobody ever does. It has 2 speeds, off and on, stop and go like hell. All right. An example. And so all that the time, that when I set the timer on a microwave, well, I guess there's 2 ways to think about it. On a normal microwave, when I set the timer, that is not a feedback loop for the system. The system is not checking to see if the center of my bowl is warm before it turns off. It is just turning off in 1 minute. It's turning off in 30 seconds, whatever I set it to. So I am the human, again, is controlling how done something is going to be. In an open loop system as a microwave, that requires a person to determine if the food has been heated to the required temperature. Whoop, lost one. What is a closed loop system? Okay, now we've talked about an open loop system. Anybody have an idea of what a closed loop system might do? A hint, it doesn't involve a human. What would a closed loop do? Come on, I've got my magic spinner. Layla, can you just imagine what a closed loop system might be compared to an open loop? It doesn't have humans for feedback. It has something else. What might that be? Layla? Okay. I'm guessing the mic isn't working. I'm not seeing anything in the chat. Oh, there she is. What's that?
Oh no, Chanelli, I was just asking. So since it works off of feedback, is it like it doesn't have like a control on it where you like control it, or?
It's not a control that I control. It's a control that controls the system, right?
Oh.
Closed loop is a control system that uses feedback from the output, the result of the operation of any system, to control the input, something put into the system, such as a resource, in order to achieve a result. Again, these definitions are very hard to understand because they are trying to make it apply to everything. So a closed loop system is a control system that uses feedback from output, the result of the operation of any system, to control the input, something put into a system, such as resources, in order to achieve a result. Okay, so if my spigot had a water meter on the end of it that went back to Montgomery County, and they said, if you use over 5,000 gallons of water in a day, we're going to shut your pipe down because we feel your pipes are leaking. That would be a closed loop system. A classic, or an example of a classic example of a closed loop system is a heating system in a home, where it has a thermostat to provide feedback when it needs to turn itself on and off. The thermostat is set at 70 degrees. When the temperature gets up to 70 degrees, the thermostat tells the system to shut down. It's going to drop down below 70 degrees and it's going to start back up. And then it's going to shut down as it gets over. So it's always going to be bouncing around right around 70. That's how the system works. I, as a human, I need to set the temperature I want, but once I have done that, I am not controlling the system. The system is on autopilot. The system is doing it all by itself, okay? So why is system thinking important? Okay, here's another fun one. You're not going to know this answer, so do not feel embarrassed. Brooklyn Prince, what do you think system thinking is?
Maybe like I don't know.
All right, no, you're not supposed to. System thinking is a weird thought, but just look at it literally. What do you think that's saying? Systems thinking is thinking about what?
Systems.
Systems, you got it, 100%. Yes. Don't shy away from George Washington's white horse. Systems thinking involves considering how every part of a system relates to others for a common purpose. Systems are used in a number of ways in technology. Systems thinking involves considering how every part of a system relates to the others for a common purpose. Now, one of my fun things as your teacher is that I have a lot of real world experience. I have not taught all my life. I have worked in other industries. I actually have a PMP certification. I am a project management professional. PMPs are people who manage large projects like construction projects, building a bridge, digging a tunnel, creating, Microsoft Word. These are all big projects and they need to be managed. When I am working on a project, you need to lay everything out in a way that every step dovetails with the next step and everything works like Swiss clockwork. So if I am building the foundation of a building and it has conduit that electrical cables are going to have to go through, I do not want to have my electricians arrive on site to put the electrical wires through the conduits in the foundation before my foundation is laid. I need to have the cement workers come first, lay the cement foundation with the conduit in it. Then once that's cured, then I have my electricians come and put that in. But I have to understand that. I have to understand that the day after they lay the cement, the workers can't arrive because it takes a little time for cement to cure. I have to be aware of every single piece of the entire system that I am building. So I am system thinking. I am trying to think of how are these different systems interrelated? How are they going to work together? How are they going to complement each other? Ideally, the system, the design that I am coming with, every system is going to work perfectly with every other system. That's going to work really well on paper until we try and get out in the field and do it, because then the plans change. Systems are used in a number of ways in technology. A system is an arrangement, pattern, or design of parts which interact with each other within the system's boundaries, form, structure, or organization, to function as a whole. So something I think of here when I was reading this is not sort of the clockwork over here, but the idea that a car motor is a system. A car motor has a pattern and a design. It has parts which interact with each other within the system's boundaries. The systems, what would the system's boundaries of a car motor be? Can anyone guess? What would the system boundaries of a car motor be? Schnell, you get to answer. What do you think the system boundaries of a car motor are?
I'm not sure.
All right, the car. That's all
Oh.
I'm thinking. And again, this is not technical, but if a motor is part of a car, right? A car is an integrated system of patterns, designs, parts which interact with each other within the system's boundaries. Everything outside of my car is not a part of my car, but everything that is a part of my car is a part of the system that works together to function as an automobile. But so my idea was that a car engine interacts with other parts of the system, but it is contained by the system. The nature, purpose of operation of the whole is always different from and more than the sum of its unassembled collection of parts. I find that it's a little interesting. So all this is basically saying is the whole is always greater than the sum of its parts. I don't believe that that is always the case. Let's say for our purposes in systems modeling it is, the whole is different from and more than the sum of the unassembled collection of parts. The reason I feel this is tricky is there's a business practice called arbitrage. Arbitrage was very popular in the 80s and 90s. It's the idea that you buy a distressed company, a company that is on the ropes and doesn't have enough money for a low price, and then you break it up into pieces and sell off those pieces for more than you paid for the company. Okay? That is making the parts worth more than the whole. But I think you understand. The way I think of this is, again, going back to my experience. I work in television and feature films. When you start a production, you are bringing all these different people who have never met each other before, never worked together, to do one common task. We are going to tell the story of a person that was in a car crash. Okay, that's our film that we're going to make. When everybody's creative energies seem to match and mesh, and the schedule works, and people work together well, you create something that is greater than the sum of its parts. You create a product that is so good, none of us as an individual could have made it. But somehow, all our creativity acted as creative multipliers, that we helped each other be more creative than we could possibly be on our own. And you created something that is greater than the sum of its parts. Okay. So knowledge of systems is a path to better understanding of how Mother Nature and human nature work. This is out in California, I believe, big wind field. Technological systems include input, processes, output, and at times feedback, depending on if it's a closed or open loop. The input consists of the resources that flow into a technological system. The process is a systematic sequence of actions that combine resources to produce an output, encoding, reproducing, designing, and propagating, for example. The output is the end result, which can have either a positive or negative impact. Output is just output. The feedback is information used to monitor or control a system. So in an open loop system, what am I, the human? Am I input, a process, output, or feedback? In an open loop system. Anybody?
The
I
feedback?
am the, oh, go ahead.
The feedback?
Right, you are. Brilliant. I am the feedback. I am the one that has to adjust the system if it's putting out too much or too little, or the toast didn't turn out right. Open loops need a human. Closed loops have something like a thermometer that is measuring the output of the system and providing feedback back into the system. So let's think about my heating system. I buy gas, again, from beautiful Washington Gas. That is my input. I have a gas line coming into my house. I have gas. I have a process that is a systematic sequence of actions that produces an output. I have a stove. When I turn the knob to the right, the stove has an igniter and it ignites the gas and creates a flame. My flame produces heat. That is the output of my gas that I'm using. I am burning my gas to make heat so I can heat a pan. The feedback in this system is me. I need to turn the knob. I need to turn the knob back off. If I turn on the knob and it doesn't light and my house fills with gas, I'm going to die. The system is not going to shut off the gas for me. Okay? So systems and universal systems model. A technology system is a combination of materials, devices, structures, information, and energy working together to solve problems and extend human capabilities. Materials like fiberglass, metal, and plastic, structures, style of the vehicle, energy, the engine or the gasoline for the engine, information, vehicle computer systems, devices, tires, wheels, etc. These are all part of a technological system. The technology systems model, input is a need or desire. I need something. All right, here's my good question. What is the technology system of a Formula One car doing to extend human capabilities? What is it allowing us to do? How is it extending our human capability? What is a Formula One car going to allow me to do? Come on, Jeremiah, you can tell me this one. What does a Formula One car do for me?
Makes you go faster.
Allows me to go fast. I want to go fast. So I buy myself a technological system in the form of a Formula One car. That is what Formula One cars are facilitating, going fast. We as humans can go fast when we run. We can't run like a Formula One car. Okay, so input, need or desire, want to go fast. Process, we combine resources. We need materials, structures, energy, information, devices. And I output a technology system. I build a Formula One car so I can fulfill my desire to go fast. All right? These are size of technology systems. My favorite is the pencil. Is the pencil a technology system? Anybody? My initial feeling was, really? But I think, again, anything made by man is technology, but it is a system because what is making the marking? Graphite. Graphite has to be encased by wood so that the person can actually hold on to it. It needs to be able to be sharpened so that you can get the graphite exposed to be able to write with it. It has an eraser to allow you to erase the graphite. So yes, a pencil is a technology system. It's a very small, very simple one, but it is. Scissors, technology system. Microscope. You know, these are going up in levels of complexity. Computers. A fire engine is more complex than a computer because a fire engine has computers in it. Space shuttle, very complex, very critical systems. People's lives are on the line. And nuclear power plants, same thing. Okay, systems often include a component that permits revising or refining the system when the feedback information suggests such an action. For example, the fuel level indicator of a car is a feedback system that lets the user know when the system needs additional fuel. But is it a closed or open system? We get a quick one on why scissors. I agree, Leslie, because they are made of component parts. They have a hinge. They are a system. You know, the pieces of it wouldn't work. Just the two pieces of scissor. You could cut something, but it's not going to cut accurately like a scissor. So a scissor is a system put together for a technological purpose. We're getting short on time, so I'm just going to say car, open system. I need to see that fuel meter to fill it. My car doesn't take itself to the gas station for me. The stability of a technological system is influenced by all the components in the system, especially those in the feedback loop. Cruise control in an automobile, for example, automatically detects and controls the speed of the car. Some delay in feedback or in functioning can cause a cycle to develop in a system. We're going to stop here, but no, cruise control is interesting because cruise control only limits the accelerator. It will keep you at a constant speed going uphill, and it will stop accelerating as you go downhill, but it does not activate your brakes. It does not actually keep your vehicle only at 30 miles an hour. When I am going down a hill with cruise control, I can go 35, I can go 40. But that's because the feedback system is not controlling braking. All right, I want to take a moment and quickly go over our project and then look at this video. Okay, so here is our project. We're going to have 10 days, so we've got time for this. Determine the components of a common communication system. These systems are called communication systems. The universal systems model includes inputs, processes, outputs, and feedback. Identify the inputs, processes, outputs, and feedback within the systems given below. Then discuss how feedback is essential to the closed loop system. List the subsystems that might support the operation of the overall system. The definition at the bottom of the document could be a help, or look it up. In the table below, describe at least one example of how a given communication system uses the universal systems model. So here we have automatic lawn sprinklers. What is the input? What is the process? What is the output? Okay, describe why feedback is not essential. List the subsystems. Next, a closed loop system. Home furnace heat system. What's the input? What is the process? What is the output? What is the feedback in this system? Describe why feedback is essential in the systems model. List the subsystems. What support of the operation of the overall system? So a subsystem is a self-contained system within a larger system, an independent system that supports the operation of a system. We're running short, so I'm just going to say, for this project, you can use the automatic lawn sprinkling system as your open loop and the home furnace system as your closed loop. If you find another system you think would be more interesting to work on, I am all for that. You might, if you're confused as to whether it is an open or a closed loop system, you can ask me. But the typical thought is, does a human have to control it? If a human has to control it, it is probably open loop. If a human does not have to control it, it is probably closed loop. Okay, now we're going to watch this video and we're going to be done. Okay, let me get this going.
Let's go to your kitchen and see how you can use feedback control to toast bread perfectly. You put a slice of bread in the toaster.
First question, toaster. Is that closed or open loop system? You can put it in the chat. Come on, it's 50-50. I'm not going to ding you for getting something wrong. Do you have to do something with a toaster?
Yes.
Yes. Thus, which system is it? Open. Perfect. All right.
Set its timer level and then turn it on. Depending on how long you toast the bread, you can get different colors. But you don't want just any color. You want to start your morning with this crispy, yummy toast. There are two reasons this might be hard. If it's your first time using the toaster, you don't know how long to toast the bread. Or assuming you do know how long to toast it, next time you might open the fridge and find a bagel or frozen bagel. These are variations that you may face, but regardless of these variations, you will still want to make perfect toast. So what if, instead of toasting the bread based on a timer setting, you toast it based on its color? But how, you might wonder? If you continuously monitor the color of the bread, you'll know when exactly to turn off the toaster. This is the basic idea behind a feedback control system. Let's try this on a slice of bread and a frozen bagel. You turn on the toaster and start monitoring your bread. When the toast reaches the color you want, you turn off the toaster.
Nice eyeballs.
Notice that you didn't have prior information on how long to toast the bread. Monitoring them allows you to tell when they have reached your desired color, so when to turn off the toaster. We will now read your mind. Don't worry, it's not to hack your accounts or anything, but just to reveal the complete feedback control structure. While you are monitoring the bread, you draw a plot in your mind. On the y-axis, you have the bread color that you're watching, and on the x-axis, you have the time. This is what you want. Then you start toasting, and this is what you see. At each time instant, you compute an error between what you see and what you want. If this error is not zero, you keep toasting. When what you see overlaps with what you want, the error becomes zero. Your yummy toast is ready, so you turn off the toaster. If we now project what you think in your mind onto the closed loop structure here, we get the complete feedback loop. This part represents the comparison you make between what you see and what you want. You compute the difference between monitored and desired bread color, and this gives you the error. Then, based on the error, you decide whether to keep the toaster on or turn it off. Next, we will switch rooms to see another example of feedback control and how it compensates for unexpected events. After eating your yummy toast, you're ready to take a warm shower. Similar to the previous example, you have a desired water temperature. By trial and error, you find the right position for the shower handle. You're planning to use this handle position for future showers as well. But what happens when someone runs the dishwasher the next time you're taking a shower? In this situation, the hot water is used up, and therefore the shower gets freezing cold. Let's go back to the time where the dishwasher isn't running yet and see how feedback control can compensate for this unexpected event. The water temperature is at your desired value. Someone runs the dishwasher. Through your skin, you sense that the water temperature drops. The error is now greater than zero. To compensate, you turn the shower handle towards the hot side, and as the temperature increases to the desired value, the error gets smaller. And the smaller the error gets, the smaller adjustments you make to the shower handle. If you now want to fully automate this process, you can use a thermocouple that measures the water temperature, and then, based on the error, the controller can adjust the shower handle. To summarize, in this video, we've seen how feedback control works, how it handles variations in the system, and how it compensates for unexpected events.
Okay,
For the next video,
we are done. Thank
don't
you.
forget
Class
to
is
buckle up
over.
because you will drive to a party.
We're
You'll
gonna
learn
stop
about the
our nice-
terminology of basic components of a feedback control system.
There we are.
Thank you.
Okay, great
Thank you.
class.
Bye. Thank you.
See you on
Bye.
Friday. Have a good day.
All right,
See you on Friday.
bye.
Bye. Have a good day.
You bet.
Hi, Mr. Swift. I just wanted to say thank you for changing my grades.
Oh,
For
no worries. No, you deserved it. You resubmitted.
Okay, thank you.
No worries. Jackson? Beverly, can I help you? Jackson? Beverly? Nelson? Jackson? Beverly? All right. Bye-bye.